Recording in
Okay, so for our second speaker today, we have Jihun, who's going to tell us about Sasaki-Einstein 5-manifolds.
All right, thank you very much for the invitation and introduction. Okay, so it's my first visit to, Baltimore since I graduated here, like it was 20 years ago. And I went to, I came here like, I think in 1996. So I met the Shokro is coming, and Florian and Vanya at the time. So we had a great time and we enjoyed a lot of good life. So in occasion of the Professor Shokrov's 70th birthday, I wish he's not here, but I wish the Professor Shokrov happiness and health and good health and happiness for future. All right, so let me start. So today I will talk about the Sasaki-Einstein 5-manifolds. So in this area, my contribution is very small. Great field in this area is actually the Boyer and Galicki and Kollár. So let me explain. Let me start. Okay.
This is my record.
Yeah, it works. All right, so a Riemannian manifold is called the Sasaki-Einstein if the cone metric defines a Kähler metric on the cone, which is defined here. And the metric G satisfies the Einstein condition. The Ricci curvature is proportional to the metric. And the Sasaki manifold is isometrically embedded into the cone, as you see. And this cone is equipped with the integrable, complex structure because it's a Kähler by definition. So it has the canonical vector field from this side, the real line side, and then this guy defines a Reef vector field because by applying this integrable complex structure to this canonical vector field, you just rotate, then it's going to be tangent vector field on M, which is called the Reef vector field. Using this the Reef vector field, it's a foliation. You can classify Sasaki manifold into 3 types. So you consider the Reef foliation, which is given by this Reef vector field. So if the orbit of this Reef vector field are all closed, then this vector field integrates into the S1 action on the M, the original, the manifold. And this vector field never vanishes. So it means the action is locally free. Right? So if this action is free, then we say this Sasakian structure is the regular. And if not, then it's locally free, just real locally free, then it's said to be the quasi-regular. And if you have the orbit, which is not all closed, then we say it's irregular. So you have these 3 types of the Sasaki manifold, which is classified by this Reef foliation. Okay, so this regular and quasi-regular case, this this Reef space of the foliation is a compact Kähler manifold or like an orbifold, depends on it's regular or quasi-regular. So if the M is our Sasaki manifold, M is the real 2n minus 1 dimensional quadriregular Sasaki-Einstein manifold, then its Leaf space is a Keller-Einstein 5-manifold of dimension m minus 1. So this is the entrance to the algebraic geometry from the Riemannian geometry. So our entrance. So this classification of 2n minus 1 dimensional quadriregular Sasaki-Einstein manifold is closely related to the study of this n minus 1 Keller-Einstein 5-manifolds. Okay. All right. So goal of my study is to determine which closed simply connected 5-manifolds allow Sasaki-Einstein structure. So it's about the Delphi ovifold, 2-dimensional 5-ovifold. So simply connected closed 5-manifolds were completely classified by Smale and Barden. Smale did it for the spin case, and the Barden did it for the non-spin case in the early 60s. So, and every simply connected Sasaki-Einstein manifold is known to be a spin. So it has a spin structure always. So spin case was what Smale did is the following. He showed this one-to-one correspondence between the finitely generated abelian groups and the closed simply connected spin 5-manifolds. So this correspondence given by this map. So when you have this finitely generated abelian groups, and then you have free part and the torsion part. And when you have the closed simply connected spin 5-manifolds, you consider this second homology groups. This homology groups, so this correspondence given by you copy the free part and then you take the twice of the torsion part. Then this gives us the one-to-one correspondence between these two categories. Huh? Spin means so in your Riemannian structure, like you consider the tangent bundle, and then you have transition map into the SON. And then this double cover spinor group. So with the co-cycle condition, if you can lift to the spin group, then we say it's a spin. If not, then the non-spin. Yeah. Spin means a spin. It has a spin structure. If you have the Sasaki-Einstein structure, then it's a spin. It must be spin. So to be precise, what's Smale proved in 60s. So for given positive integer m, so there is a unique closed simply connected spinable 5-dimensional manifold M, whose second integral homology group is like this. And furthermore, every closed simply connected spinable 5-dimensional manifold is like this. So here M infinity means the S2, the 2-dimensional sphere times the 3-dimensional sphere. And this is the connected sum. And it's like this fundamental theorem of finitely generated abelian groups. So it's exactly the same as what that, right? So we have the classification for the simply connected 5-manifolds, right? So among them, so we want to determine which one allows this Sasaki-Einstein structure, right? Still huge area, but in 20 years ago, Kollár restricted this such an area. So he proved this theorem. So it says when you have the closed simply connected 5-manifold with a positive Sasaki-Einstein structure, then the second torsion subgroup of this second homology group is determined by this differential orbifold, and this torsion part must be one of the following. See here, like this and this and this and this type and this type. That's all. So you see the torsion part of this. This gives us a huge, the strict restriction. And also, he proved there some like structure theorems. He proved there more about this second homology groups. So if the order of the torsion is at least 12, then the rank should be free part. The rank of the free part must be at most 8. And if it has no free part and the torsion part is like this, the second case, then this order of the this torsion must be not divisible by 30. And we have in this case you must have the rank like this and like this and this. So that restricts the area like a lot. All right, so let me summarize this in this table. So this is the candidate. The Snell 5-manifold is the simply connected spinable 5-manifolds. That's we call this Snell manifold. So here I list, we get the second page and next page, I listed the possible candidate who can allow this Sasaki-Einstein match. So the first page is for the case when the homology group has no free part, which is called the rational homology group. The rational homologous spheres case. So this is the only possible candidate for the Sasaki-Einstein metric. And if you have a positive rank, then you have these possibilities. So here your torsion part is restricted. Yeah. So we want to check which one has among this possible candidates, which one allows the Sasaki-Einstein metric, which one cannot. So that's their main task. So as I told you in the beginning, this area is cultivated by the Boyer, Galicki, and Kollár. So they introduced the method, which actually they introduced in the 60s by Kobayashi, and then Boyer, Galicki, and Kollár, they developed this method. So for this method, we consider Cypher's S1 bundle actually over the orbifold, but for simplicity for this talk. So we here consider only links of the weighted hypersurface singularities. These are the simple example of the Cypher S1 bundles over corresponding the weighted projective hypersurface. So you consider a quasi-smooth Fano hypersurface in a weighted project space, PW. Weights are here, right? And which defined via this quasi-homogeneous polynomial. And this polynomial defines the hypersurface. The affine cone, affine hypersurface in CM+1, smooth outside the origin because our assumption is a quasi-smooth. Then we define the link of this hypersurface X, which is the intersection of this affine hypersurface with the unisphere centered at the origin in the CM+1. And this link is a smooth compact spin manifold of dimension 2n-1. Okay. And if n is 3, then it's a simply connected. Known to be simply connected, which was proven by Miller in 60s. All right, then what Kobayashi and Galicki and Kollár proved is the following. If X is the O-before Einstein metric downstairs, then this link has the Sasaki-Einstein metric. So that's the way to find the construct the Sasaki-Einstein metric on the link. All right, so to find the simply connected Sasaki-Einstein 5-manifolds from their factor O-befores. So we consider, as before, we consider this surface, weighted surface in weighted project space, P, A0, A1, A2, A3. We did this final condition. All right, then the problem here is we first determine the topological type of this link given by this hypersurface, two-dimensional hypersurface. But what, according to Smale, this topological type can be determined by this second homology groups, right? But still we have problem because this hypersurface is given by equation. And the second homology group is about the geometric things. You have to extract from this equation. You have to extract the topological data. So in 60s, like Miller, Ehrlich, and Randall, they produce. They use some like a formula which determine this second integral homology group of the link. So which given by weights and the degrees. So D is given and weights are given, right? Just they have some formula for this. But in 2005, in the Kollár's paper, he proved this. So you consider this hypersurface as the O-before. So this is the O-before structure. So this is the branch divisor. Right. Then this free part is determined by the length, current length of the hypersurface. Okay. And this torsion part is determined by this branch divisor. So genus of this divisor, and the ramification index determines the order of this torsion. So, and then like to apply the Kobayashi, Galicki Kollár method, you have to determine whether this O-before allows the Einstein metric or not. Right. So you have this at the bottom you have this derivation O-before, and the upstairs you have S1 bundle. So this is your 5-manifold, the target space. Right? So you have to determine the bottom has the Einstein or not. So, all right, so you have to determine this problem. So at the beginning, like they used this alpine variant, right? So nowadays like this alpha and beta like delta invariant is now like among algebraic geometers like it's very available. But yeah, let me briefly introduce. So alpine invariant of the Fano variety measures how singular members in the fully anti-canonical linear system, right? So actually known to be was introduced by Gantian like the 80s. So definition is like this. So you collect all rational numbers such that this pair X, CD plus the delta is log canonical for every effective Q divided D, which is equivalent to this minus KX plus delta. And then you take the split. This is the definition, right? And the reason why the Tian introduced this because of this. So this n-dimensional Fano O-before allows the overfold Taylor-Einstein metric if this inequality is satisfied. Right. So using this method, like Galicki, Kollár found many like Sasaki-Einstein simply connected 5-manifold. So let me list what is at the time what are done and what is not done. So in the rational homogeneous sphere case, so they proved the up to here or allows the Sasaki-Einstein metric, but they couldn't. They just checked the like up to 7 and then except 4, and then they couldn't determine the if any swatch in this case. And for the positive rank case, so like many parts of, I mean, done. I mean, they did like the 99. I mean, they're almost 90%. So they determined like many areas. Like this is done and done and done. Right. So let me give you some example. So let's start with the simplest one. So first example is the future surface of degree 1, smooth one, which is the hypersurface of the weighted hypersurface of degree 6 in 1, 1, 1, 2, 3. And nowadays, like this alpha invariant is easily calculated. So which known to be at least 5 or 6. So that means you have the Taylor-Einstein on this future surface, right? And their future surface has the rank 9, right? So it gives us like a Sasaki-Einstein metric of 8 times m infinity, right? And this one is a singular, so you consider this a singular weighted hypersurface in this weighted project space, all right? And you can also like compute here this alpha invariant, and I briefly compute. I think this is 1, if I'm correct. Right, and that implies the Taylor-Einstein metric on this hypersurface, and this guy has a rank 3 using this Miller and this Olligen-Lander formula, and 3, and that gives us a Sasaki-Einstein metric on this 5-manifold. Right, and now you consider this hypersurface. 36 in this weighted hypersurface, but this is not well-posed. That means you have a non-trivial like French divisor, right? So you have this as an obifold. You may consider this guy as this log-del project surface. So this is the 6 is the ramification index, and the CY is the French divisor. CY means I always use the weighted homogeneous coordinate x, y, z, w. So CY means this one is given by the y equal to 0, this section. Right, and then you can compute this alpha invariant, then turn out to be 1. Then this gives us obifold Taylor-Einstein metric on this obifold, and you get this, and you can compute this rank using by the formula. It has a rank 1. That means you don't have any torsion. I mean, your free part in the H2. You only have the torsion, so which is M6. Here's the example by Kollár. So he considered this a Hirschberg surface, and then here E is the negative section of this Hirschberg surface, and F is the fiber. And you take the smooth member in this linear system. Then this guy is the ample if M is big enough. M is if m is the bigger than 2n. Then this is the temperature, and you can construct the S1 bundle actually on this OB4. And then you compute this alpha invariant and then turn out to be 1. That means you have a Keller-Einstein, OB4 Keller-Einstein metric on this OB4. Right? Then you have the Sasaki-Einstein metric on this 5-manifold. Here, this guy has the rank 2, the curve number 2, right? And this curve is the genus n+2. So it increases. So that's why you can have this the Sasaki-Einstein metric on the series of this 5-manifolds. Let me give you one more example. So this is the example by Krzysztof and Martinez-Galicki. They didn't mean it. I think that this result is 5 or 6 years ago. They want to compute the exact alpha invariant for this type of the log temperature. So they compute the all possible values for this. So you consider their feature surface of degree 9 minus r. So you just blow up r points in general position, right? And you consider smooth membrane descent in this anti-canonical linear system. Then actually they compute this number for the 1 minus beta, for the 1 minus beta. But here for this case, their formula tells us that this number is always bigger than 2/3. This case. So, and we know this log temperature surface allows the smooth S1 bundle. So there's a Sasaki-Einstein structure. So that implies this and this has the rank r+1. So you have this free part, and this gives us a torsion part because this is a genus 1, and this is the order of this torsion part. So you have this, and that implies this, right? Because of this form. This guy determines this topological type, right? So it used to be like this, their work according to about this, before this, we have this answers, but it clean up this answers like this. So now for every m, n is 2, so you have always the Sasaki-Einstein metric. All right, and this after we enter the 21st century, so this K-spherical issues developed a lot. The rapidly. So in 2012, this theorem was announced. This seminal work was announced by Chan Donaldson's son and Tian. So what they proved is the Farnow manifold, that means the Keller-Einstein metric, if and only if. It's a K polystable, right? And it was generalized by many people, Berman and Li Tian Wang and Yu Chu Shang, right? It generalized to the log Farnow pairs. So it's true for this category. So log Farnow allows the Keller-Einstein if and only K polystable. But still hard to determine whether given Farnow variety is the K polystable or not. So at the beginning it was hard, but the 2016, Fujita and Odaka introduced this new invariant, which is called the delta invariant, as the K stability indicator. So it gave us criteria. So let me briefly introduce. even though almost all you know about this. So we consider Q Fano variety X, and let's say M is the positive integer. Then you consider this vector space, anti-Fourier canonical system, this linear system. And then you take the basis of this space, right? And then, for this section, you take the effective divisor, and you normalize this divisor, and then you take the average. This kind of divisor is called the M basis type. Then you measure the singularity of this divisor using the low canonical threshold, and then you take the infimum. Right, that's M's delta invariant, and then you take the limit exists by Blumen-Johnson. So that is called the delta invariant of the X, right? And you can also define the X delta, the log Fano case, delta invariant, same way. Or currently you can use this formula, which was introduced in Vanestor first day. So for any divisor E over X, you consider log discrepancy of the E, and also you consider volume, average volume, expected volume, and then you take the fraction of this number, and then you take the infimum, right? Among this division E, and that's the other thing.
Looks like for in the personality condition, but
Yeah. Yeah, maybe.
which is reasonable to consider with everything, but for your application.
Yeah. All right, so Fujita, Odaka, and Blumen-Johnson, what they proved is the following. So K stable, this log pair is the K stable in front of one. This delta is strictly bigger than 1, and semi-stable at least 1, right? So it's tempting, right? So we can apply this method to the Sasaki-Einstein problem. So I consider this hypersurface 4n plus 2 in this weighted project space, right? So this is now well formed, and it has the order 2 group action, right? And the branch divisor given by this coordinate W. The branching divisor given by the W equal to 0, right? So as an obifold Xn, you may consider this log pair. So you reduce this weight by 2, and then you will get the same variety, not as an obifold, but as a variety of the some peak, and then you have the branch divisor here, right? Right. And then this guy has the rank 1, and the CW has the genus N. Right? So this link of the Xn must be N times M2. Right? So then we approximate this delta invariant. This work was 3 years ago. So not so many machineries were introduced. So we used the Newton polyton method, some very complicated way, but nowadays it's a very simple. So we succeed in the approximate this number, and turn out to be bigger than 1. That means K stable, this guy. So you get the Galicki-Einstein, before Galicki-Einstein metric. Again, you have the Sasaki-Einstein metric on this N and 2. And we also consider this guy SN, hypersurface of the degree 2 times 2n plus 1, and in this weighted project space. And then we consider same like irreducible divisor given by W. And we consider this this OB-fold. This is again the branch divisor and your variety. And we can prove that this delta is strictly bigger than 1. Then this is the case stable again, and you have the Einstein metric here, right? And this time, this guy has the rank 2, rank 3. Current rank is 3, and genus is the N. Okay, so you have the Sasaki-Einstein metric on this series of the 5-manifolds. Okay. So we add the 2 series of the Sasaki-Einstein 5-manifolds in the list. So we have this and we have this. Right? So this complete this completely determines which rational homology 5 still allow Sasaki-Einstein metric or not. So previous work was up to here. They couldn't decide whether for every n, this guy is the Sasaki-Einstein or not. But this time, like we determined we verified that this guy always the Sasaki allows the Sasaki-Einstein metric. Right. So during last 3 years, like this technologies in the case stability is advanced rapidly, right? So I spot some theorem in this Calabi problem in the Farmer's report, which was written by many people, including Vanya and Araujo and Castravet. So they have this term. So X is the Farmer variety with the character singularity, and this B is the divisor, which gives us the branch divisor and the overfold, but which is the proportional to the anti-canonical divisor with a certain condition like this. And if this condition is satisfied, then this guy is the case stable. Right. So let's see. This is one condition proportional to the anti-canonical divisor, and some numerical conditions like this. All right. Let's get back to this Vanya and Ass's work. So they consider this like R points in general position, and they blow up, and then they consider this smooth member in this anti-canonical linear system. Right. So it's a proportional, right? So it satisfies this numerical condition which required here. So they are all case stable. So now it's simple. So they give us this Sasaki-Einstein metric on this this 5 minutes. And this is another application. So you consider this 1,1n weighted project space. And you have a quasi-smooth curve of the degree 2n plus 1. All right, so delta invariant of this weighted plane is 3 over n plus 2. Right? This is a toric, so you can easily compute. And you calculated this number, which is required here for the theorem, and all satisfied. So this is case stable. And this gives us this Sasaki-Einstein metric. Right? It's very simple now. Right. So let me summarize the current status of the Sasaki-Einstein 5-manifolds. So rational homology case it's done. So we completely determined which rational homologous sphere allows the Sasaki-Einstein structure or not. So this is all done. Right. All right, so everything is done in black. I mean, the black guys here, like we know everything. So we completely determined which one has this Sasaki-Einstein metric or not. But the problem is in red one, which means the red one here. So we don't have any idea here. And we have partial, partial results only. So here it's known that if K is 1, M infinity, plus, this connected some 2 times M3 and 3 times M3, they allows the Einstein the Sasaki-Einstein metric. But if K is strictly bigger than 1, we don't know. And for M2 case, so we know when I missed the one case. So when K is 0, 1, 2, we know the answer. It allows the Einstein metric. Sasaki-Einstein metric. But if K is bigger than 2, then we don't know. So let me extract the remaining case. So this is the remaining candidate, which possibly allows the Einstein metric, the Sasaki-Einstein metric. So this is the case, and this, and this. So, but there are some small pieces which shows there are some 5-manifolds among this can allow the Sasaki-Einstein metric. So here clue means that this 3 guys allows the Sasaki-Einstein metric. So I made some conjecture. One of them is already proposed by Galicki. So let's say M is our closed simply connected 5-manifold M. And for the first conjecture, it's like this: if M has the second Betti number, is N is 9, then it admits the Sasaki-Einstein metric if and only if it has no torsion. That's the first conjecture. And second conjecture, if M has the second Betti number N is 2, then this type of the torsion cannot appear. That's the second conjecture. And the last conjecture is this type of, if K is the M most 8, then this admits the Sasaki-Einstein metric. That's the third conjecture. So if you collect this conjecture, then you will have this table. So like this. So we guess that this type of the first 2 types of the Small 5-manifolds never allow the Sasaki-Einstein metric, and the last type also never allow the Sasaki-Einstein metric. And this third type, we guess only up to K equal to 8, they allow the Sasaki-Einstein metric. If K is bigger than 8, then no way. That's our guess. But we don't have any clue, and we stuck here. So we have no idea how to prove how to improve this table. All right, let me stop here. Thank you very much.
Any questions?
And so we look at the basic homogeneous case.
Yeah.
then are there some candidates where you can put this patients cannot decide?
With this-
if it's stable or not?
Yeah, this all the candidate comes from the the Galicki list. So I tried all the things, and then on their list they don't have any candidate for the other remaining cases. So that's why. So in particular,
So they do data here and will pay hypersurfaces, or they are just not computer search matter.
I think they do this computer search. So
I see.
so and they don't have any like candidates for the this and this.
Yeah.
So that's why I believe that there is no such things. And for this third part, so we have some examples which allows this, which probably implies this penalized on this type.
So in the extreme cases, there were some where uniqueness was.
Yeah.
You have some more examples of that?
No, I will do in that area.
It's a Zoom question. It says for the simply connected 5-manifolds, does the associated isolated three-fold singularity have a special property? Is it always local possession?
No, the answer is not.
No, yeah, no, it's about three-fold similarity. So why three-fold related to the 7-dimensional things, not the 5-dimensional things. No.
So do we know something about the rational homology in 7 speed?
Rational homology.
Dimension 7.
We don't know because I mean, this dimension 5 is special because you have the classification by smell. So you can like approach this problem due to him like it's very concrete. But yeah, 7-dimensional, I don't know, like they have.
So there's no homological concept.
No idea.
There are some examples. Yeah. I actually don't know that.
Yeah, maybe one the drawing in homological.
Finally, does associate the also with zero. I didn't get the point.
Can you read it?
So I don't know what this means, but I cannot answer to this question. I think link is the complete intersection or something. I have no idea. Sorry.
Okay, if there's no further questions,